Modern life is totally intertwined with the innovative products of the electronic revolution. But just what are the powerful engines that enable these products to work? We find them hidden in small packages, attached to circuit boards. They are microchips, made on tiny pieces of semiconducting materials, usually silicon. A chip can contain many millions of miniature electronic devices, all wired together to form an integrated circuit. State-of-the-art chips contain billions of components. But what exactly are integrated circuits? And how are they made? Making the microchip at the Limits 3 will answer these questions and reveal a manufacturing process that pushes the limits of technology, just as it will push your imagination. Now let's look at this astounding manufacturing phenomenon called microchip fabrication, a series of demanding process steps that produces billions of chips in factories all around the world. Microchip manufacturing is divided into 4 distinct stages. Stage 1, material preparation, extracts and purifies the semiconducting material. Next comes the growing of crystals from the semiconducting material and preparation of thin discs called wafers. In Stage 3, microchip fabrication, the circuit components are formed in and on the wafer surface. Finally, the wafer is separated into individual chips, also called die, and placed in protective packages. This is called packaging or assembly. Because microchips are extremely sensitive to incredibly small amounts of contaminants, a necessary first step in wafer fabrication is the design and construction of a clean room, which exceeds the cleanliness of a hospital operating room. Every aspect of a chip fabrication area, or fab, is designed and controlled to protect the wafers from unwanted contamination. Fabricating integrated circuits requires the formation of thin films of various materials on the wafer surface. The operations used to create thin films are referred to as layering processes. These layers perform different circuit functions. Some are conductors. Some are insulators. Still others may be added layers of semiconducting material. Patterning is the most demanding and costly semiconductor manufacturing operation. There are 5 basic steps to the patterning operation. The first, photoresist coat, begins with sequential dehydration, priming, and baking steps. These are followed by the application of photoresist in a spin process and another baking step to drive off the photoresist solvents. In step 2, the critical alignment and exposure procedure, the pattern on a reticle or photomask is aligned to the wafer and then transferred into the photoresist layer using one of several different approaches. After alignment and exposure, the photoresist layer has regions of exposed and unexposed resist. Bringing out the pattern in the resist layer occurs during the development process. Dry etch takes place in plasma etch systems, where the patterned photoresist acts as an etch stencil. The doping process drives very small amounts of dopants into the wafer surface through openings created in a patterning operation. Doping alters the conductivity of semiconducting materials. The dopants create electrically active N and P-type regions in the wafer surface. Ion implantation is the most commonly used doping method. The deposition of many thin layers is needed in building integrated circuit structures. A deposited layer may be a semiconducting layer, such as silicon, an insulating material such as silicon dioxide or silicon nitride, or a conducting layer of metal such as aluminum, copper, or tungsten. Chemical vapor deposition, or CVD, is often used to deposit silicon and dielectric layers. Insulating materials are referred to as dielectrics. Many device structures are built on the wafer surface using CVD layers. This results in height variations that cause focus problems for subsequent patterning operations. The solution to this problem is to flatten or planarize the surface of the insulating layer, which is deposited over the structures on the wafer surface. However, the most important planarizing technique is chemical mechanical polishing, or CMP. CMP combines chemical action with light mechanical polishing. Metal layers, deposited and patterned on the wafer surface, are used to connect the individual components, creating an integrated circuit. The most common deposition technique for metals is sputtering. Sputtering is a physical process and a form of PVD, physical vapor deposition. Sputtering is similar to freeing pieces from a concrete wall using a sandblaster. Another method of depositing a metal on the wafer is electrochemical deposition, ECD, also referred to as electroplating. An important use of ECD is to deposit copper layers. An important issue in the multi-level wiring structure is the dielectric constant, called K, of the material used for the insulating layers. The metal oxide semiconductor, or MOS transistor, is a key circuit component used in very large numbers as a switch or amplifier. It has a simple sandwich structure. The main parts of the transistor are the source, drain, and gate. What you have just seen is one of the technical wonders of the modern world, the microchip manufacturing process. It's a series of high-tech steps that requires the absolute limit in precision machines and state-of-the-art materials. It's a process that produces the miniature engines that drive the information age. The semiconductor industry is truly at the limits of modern technology.